answers. У нас є одне запитання з інтернету до професора Куксенка. Ваш результати по збільшення ємкості конденсаторів, акумуляторів, ви запатентували це? Ну, справа в тім, що висока ємність...
High problem. The main problem is low accumulated reversible capacity, and our materials differ from other materials. Unique low accumulated reversible capacity. This material was not patented because in Ukraine we don't see any sense in obtaining patent.
Thank you very much. Let me invite to microphone for the next talk Dr. Indutnyy from Lashkaryov Institute of Semiconductor Physics.
Добрий день. Я представляю технологію інтерференційної нанолithography з використанням високозрільних
nanolithography for high-resistant chalcogenide photoresistors. The nanolithography is the basic technology for micro and optoelectronics photonics for many years. In the recent years, due to a switch of nanometer sizes, a very important role is played by new nanolithographic processes, nano printing, integrational lithography, and other methodologies. So I will try to speak to be as concise as possible. The cheapest technological realization is intervention lithography, which doesn't require interference lithography, but doesn't require expensive equipment. Such structures can be used in spectral devices, elements of integral optics, optoelectronics, microelectronics, optic sensors, and others. A simplified schematics of the technology is shown on the figure 1. This is a base with photoresistor. B, interference field is formed by several coherent beams, laser beams. And this is a selective treatment with relief structure. If we add to interference lithography and immersion, we can decrease the size of critical elements to sub 100 nanometers, and we can form a nanostructure here. To organize this method, we need photoresistors with unique properties. For instance, nanometers the standard photoresistors do not comply with these requirements, but the Institute of Physics of Semiconductors developed inorganic photoresistors based on chalcogenide semiconductors, which are characterized by 10 nanometers, the wide spectral band of sensitivity, and ability to form complex form bases. Functional layers of micron and the wave refraction allows to have an immersive functions. So comparing this with our photoresistors allowed us to develop an effective technology to form periodical nanostructures with spatial fractures of 8,000 per nanometer. The technology of production based on chalcogenide photoresistors of diffraction grades 3600 lines per millimeters to produce optic disc and so on. It's already protected by patent, and already small-scale production is planned by corporation Arsenal that are planning to produce spectral devices using these elements. The study of characteristics of these materials the first batch of elements show that they correspond, they match the best analogies of the other countries, and which managed to increase the spectral frequency and they decrease the size. So we developed a nanolithography technology of a new type. These figures show the grades with spectral frequency 350 lines per millimeter and grating and its polymer copy, which enables us to produce large-scale copies. And this is a liquid phase immersion, this is solid phase immersion. This is 90 nanometers, 70 nanometers, the length of line. So this is a nanostructure. Interference lithography allows to obtain not only a simple structure, but more complex structures with multiple exposition or exposition with several beams. And this shows some minor binary structures with a double exposition and with a slope of 90 degrees, high frequency and more low frequency, submicron, 400 nanometers with rectangular angle. So these structures can be used as optical elements, diffraction of sub-wavelength, or the templates for copying, and so on. We also change the mode of treatment. We can form a lithographic mask. So the structure with holes through which we can treat the bases or functional layers. The further figures show examples of how such structures are formed with anisotropic treatment and the different shapes of the grating, and it's clear that we can vary this shape. Also, these are binary structures, various frequencies. Varying the exposition, we can adjust the depth of the modulation, the shape, and of course, for different applications. The next example is forming the high-frequency structures of dielectrics. This is a silicon oxide layer, and there are these holes that we built, and we can grow the nanorods, silicon nanorods, and use it as a template. Another example, the metallic structures. This example shows the structure of golden stripes, 15 nanometers thick. We can also adjust various. We can adjust frequency and the width of each stripe using plasma resonance and increase the efficiency of photovoltaic elements. As I said before, these relief structures can be used as templates to build further 3D structures, the photon catchers, and so on. And using this glance single deposition, we obtain this structure on a template produced by produced with interference nanolithography. So there were some examples of the structures that can be obtained with this technology of nanolithography, and now some of the practical applications. The main application for This nanolithography is producing optical elements for spectral devices, optical sensors, filters, and integral optics for passive elements mostly, and diffraction gratings are used as for spectral devices, spectral measurement devices, as well as sensors and optical elements. The expected properties. The area of single exposure. This is because of our 1 watt laser. By increasing the capacity, the power, we can increase the area. The spatial frequency, the periodic relief structures, up to 8,000 lines per nanometers. By increasing the wavelength, we can increase the spatial frequency as well. And then the critical sizes will be decreased to 40 nanometers. And another advantage, we developed the technology by optimizing the selective, by using the germanium chalcogenide, which do not contain toxic elements, unlike traditional chalcogenide. Which used arsenic elements. And another advantage that we use reduce the surface roughness. And economic advantages that we measured together with Arsenal, the factory that plans to produce these gratings, is 1.5 to 3 times lower price compared with our foreign competitors. Only in grades. These are American companies listed here. Now patenting. We obtained about 30 patents, including foreign patents, 2 more patents. Proposals, licensing and joint production. These are some contacts. Thank you for attention. Are there any questions? In the Institute of Physics, Dr. Smirnova has been doing works in photopolymer materials with additives, nanoparticles. Could you compare possibly your technology with the technology of creating similar diffraction elements with the use of photopolymers? I know very well the works of Madame Smirnova. I was an opponent during her doctor's thesis. They're different things. We have relief structures, lithography, the masks. No, I mean efficiency of both. The photopolymers are used for recording 3D spatial holograms. They cannot be compared. These are different devices. While diffractional elements, both are diffractional. No, 3D spatial are relief phase objects. But their principle of action is different. Even different interference, everything. The grating is still grating, whether it's 2D or 3D. As for gratings, I'm talking about the products. All the gratings that are produced are relief phase. And we're planning to, together with Arsenal, to produce these kind of gratings. And I brought some samples with me. As for photopolymers, spectral devices, such gratings are not installed. Are there any business questions to the author? Could you tell us, please, what is the segment of market that you are counting for? How many such gratings are produced? In Ukraine, the segment of market is not too big, about 100 elements. Now, if there wasn't a proposition as far as licensing is concerned, a joint project, a wider markets, modern market, in order to aim there, we need to invest somewhat. For Ukraine, we're capable of sustaining production. Why do you want to decrease the price? You said that your product is cheaper. Okay, for competitiveness on the market. For existing production in Ukraine, what if we start up the company, or so why do you invest in intellectual property, and why do you want to decrease the price?
Okay, if no questions, let me switch to another presenter.